right. So my name is Zach Shurek-Conti, and I'm a Turing Research Fellow at the Island Turing Institute in London, currently calling you from my home country, Malta. Not so sunny today. I'd also like to introduce my colleagues and co-organizers of the seminar series. So Andrea Pizzoferrato, who is a visiting academic at the Island Turing Institute and the University of Bath, and Davor Duntovic, who is a PhD enrichment student also at the Turing. For those of you who are not familiar with the Island Turing Institute, this is UK's National Institute for Data Science and AI. On a side note, if any of you are interested in sharing your work with us in one of our seminars, please do get in touch with either of us. We'd be happy to find the right slot and we can talk from there. As for the format of the seminar, our speaker will share his work for around 40 to 45 minutes, followed by Q&A, which may be done in person or via the chat function. So without further ado, I'll ask my colleague, Andrea, to introduce our speaker for today, and thank you all.
Oh, thank you, Zach. So our speaker today is Qiaofeng Li, who is a postdoctoral associate at the Department of Engineering at MIT, working on physics-informed deep learning and uncertainty quantification. Prior to this, he held postdoctoral positions at UCLA and Virginia Tech, where he worked on several marine energy conversion projects, and Tsinghua University and Harbin Institute of Technology in China, where he obtained degrees in engineering mechanics. In his research, he emphasizes the role of physics-guided interpretability and the generalizability in achieving robust characterization and uncertainty quantifications of dynamical systems. Without further ado, thank you again, Qiaofeng, for your participation, and the floor is yours.
Yeah, thank you. Thank you for the invitation and the introduction. It's an honor to be here. So today my topic is promoting data efficiency of deep learning for dynamical systems. And it's a joint work with Professor Khalid, Professor Vani, and Dr. Tianyi Wang at UCLA. I'm sorry. So in physics and daily life, we encounter a lot of dynamical systems like double pendulum, climate dynamics, and well-studied cylinder wake flow. And these dynamical systems, they are normally like expressed as ordinary differential equations or partial differential equations. And we will assume that we can observe the state of the dynamical system. And as the time evolves, we can like observe a new state. And basically you get a trajectory in the state space. So if this is the case, then we have, let's assume that y of a dimensional d is a state vector of the system, and t is time. And if using this work just focus on ordinary differential equations, so we can let's assume that we can express the dynamical system in this form. This F is the derivative field of the dynamical system, and phi is the physical parameters of the system. So if we can do this, then basically we can start from any given initial condition. We can integrate in time and calculate the state of the dynamical system at any time t. So if we have the this true physics of the dynamical system, as I said, we can do the integration in time, and we can get a snapshots of the state of the dynamic system at time t1 all the way to let's say tn. And then neural OD or neural ordinary differential equation becomes a natural tool to learn the physics of such kind of system in a data-driven manner. So we can assume that we want a neural network denoted by f parameterized by the weights theta. We ask this neural network to mimic the physics of the true system. So this is supposed to be mimicking the derivative field. And we can also, starting from the same initial condition, do the integration in time and get the snapshots of the, of course, the prediction snapshots of the dynamical system. And if the neural network is doing a good job, then this prediction should be matching the ground truth. So if there's a deviation from the prediction and the ground truth, then we can optimize the neural network to decrease this deviation. So the weights of the neural network can be optimized based on the loss between the prediction and the ground truth. And you can use backpropagation to calculate the gradient of theta. So this kind of tool is very well suited for dynamical systems where it's a continuous time process, and it can elegantly accommodate irregular or partial observations. I mean that these time snapshots, it doesn't have to be evenly distributed in time. You can have like variable time steps. And it's very straightforward to incorporate the physical priors that are already in the form of differential equations. I mean, in the letter, I will show like Newton's second law of motion and like Euclidean symmetry. Those have to be incorporated in a derivative form. For example, like Euclidean symmetry, that this kind of symmetry, although it's it can be embedded in the derivative field, but you don't have that in the solution field. You can easily have an asymmetric initial condition that will break the symmetry. So in the part one, there are two parts in this talk. In the part one, I will talk about how to use neural ODE to efficiently construct a reduced order model for Slinky. And I will show that neural ODE by itself is not enough. We need add more ingredients. So this Slinky basically is a toy. It's a very long helical slender rod, and if you fully stretch it, it will be like meters. So from the first principles, if we want to model the physics of the Slinky, we use a method called discrete elastic rod. So basically, for this very long rod, we discretize it into many small segments, and we can calculate the bending, torsion, and stretching energy between the little segments. And the mathematical tool we use is called discrete differential geometry. Basically, it's a tool to capture the geometric nonlinearity in the deformation, and it's good at capturing the torsion, bending, coupling between the little segments. I wouldn't go into the mathematical details, but let's say you can write this nonlinear energy analytically, and you can calculate the gradient with respect to the degrees of freedom at the nodes. Then basically you can use Newton's method to do the dynamics update. So so our task here is to construct a reduced order model for the 3D Slinky. So there's some motivation here. I wouldn't talk too much about it, but the bacteria in nature, they kind of like develop this kind of a helical structure as their flagella. So basically, these guys, they attach Slinky, a very soft Slinky at their end, and they use biological motors to rotate that Slinky. As it rotates, it will generate a propulsion force in fluid, so that basically the bacteria can move in fluid like water or whatever. So this is kind of like the motivation. If we can build a reduced order model for the Slinky stuff, we can use it to design like miniature robotics to mimic the bacteria stuff. Yeah. So let's go back to the reduced order modeling. So let's say that we have this 3D Slinky in the physical space. We have a state, like the position and the velocity for the Slinky, and using the first principle tool I talked about, DER, we can do the dynamics update to the next time step. So we want to find a encoder so that I can map this state from the physical space to a reduced order space, or what you call it latent space, and do the dynamics update in the latent space, calculate the state at the next time step, and then use a decoder to map it back or to the original 3D physical space. So the encoder here is very easy. We can just it's just the mapping into the plane. So let's say I have 3 cycles of the Slinky. Then for each cycle, I have a top vertex and the bottom vertex. Basically, I can map it into the X or Y plane. Then I get, for each of the cycle, I get a bar. So these 3 bars, they are called a triplet, basically 3 adjacent bars. And for each bar, I have only 3 degrees of freedom. The X and Y of the center point and the rotation angle alpha. And for, let's say, after several steps of dynamics update, I have these 3 bars. Then I can, my decoder is just like a geometric method to draw half circles and reconstruct this helical shape. So that's decoder and encoder. So you can see that if for the 3D simulation, if for these 3 cycles, if I discretize it into 16 nodes, basically I have 3 cycles, 16 nodes per cycle. And for each node, I have 4 degrees of freedom. So that's roughly 190 degrees of freedom for just the 3 cycles. And for this triplet, 2D triplet formulation, I only have 3 by 3, 9 degrees of freedom. So there's a large drop in the number of degrees of freedom. So you expect, if I can do this in 2D, you expect a very large computational acceleration. So the question becomes how to do this dynamics update in the latent space. As I introduced, there is a strong geometric nonlinearity and coupling between binding and torsion. So you don't have an analytical expression for the 2D dynamics update. So we propose to use a neural network to learn it. Okay, so the first idea we try is a very naive idea. Is just using convolutional neural network. It's a pure data-driven approach. So I'm constructing a neural network that takes the coordinates of the triplet as input, basically 9 numbers at some time ti. And I ask my neural network to predict the location of the center bar at the next time step, 3 numbers. So input is 9 numbers, output is 3 numbers. And if I can do this with a convolutional neural network, basically I can use this neural network to convolute along this Slinky. So I can extract each triplet and input it into the neural network, and it will output the location of the center bar at the next location. And I convolute along the Slinky. I can get the location of every bar at the next time step. So actually this worked pretty well. So you can see that here I have, I don't know if this is 40 or 76, but basically a long Slinky and with both ends fixed, drop under gravity from an initial horizontal. I don't know if you can see this smoothly. So basically, the left is created by the DER method. The right is CNN. So you can see it's roughly matching pretty good. But after training, we fix the neural network and do generalization testing. So you can see that I basically changed the orientation, initial condition, and the boundary condition for the Slinky. The simulation is like far from accurate. So this kind of pure data-driven approach it is good in training, but it cannot generalize. So we have a lot of failed attempts, but I will talk about in the ablation study. But this is what we eventually arrived at. This is called the Euclidean symmetric neural network. So we are trying to learn the derivative field instead of the solution field. So for this specific second order dynamical system, the derivative field means the force field for that system. So here W is the generalized coordinates of the state of the Slinky, including like U is the position, U dot is the velocity of the dynamical system. So this basically here we are trying M is the initial matrix for the Slinky, And FW is what we are asking the neural network to learn, the force field. So that if we can learn this, we can just use Newton's update to for the dynamics update of Slinky. And we can ask a naive neural network to directly predict the force given some ground truth. Let's say I have a lot of like configuration, coordinates and force pairs. I can directly learn the force, but we want to further enforce conservation for the energy and enforce Euclidean symmetry for the and both the energy field and the force field. So I will talk about how to do this, but eventually we arrived at a solution. So we induce the force field from an energy field. So first we ask the neural network to build an energy field for me, and then use backpropagation to induce a force field. And we want Euclidean symmetries for both the elastic energy and the force. I mean, Euclidean invariance for the energy field and Euclidean equivariance for the force field. So here, Euclidean transformation means that I can rotate and the triplet and translate the triplet and do reflection with respect to x and the y axis. And in the paper we published, we call this Carroll transformation. So there are two core ingredients for the Euclidean symmetric neural network. The first one is called localized interaction. So basically, the motion of one cycle of Slinky is essentially dictated by the immediate neighbors before and after it. So that's why we have this triplet formulation. We limit the neural network input to 3 cycles of the Slinky. That's a triplet. So we ask the neural network to predict the elastic force only for the middle cycle. So how to do this? Given any coordinates of the position of a triplet, basically 9 numbers, we first calculate the relative position between the bars. So that will get rid of the rigid body motion, like the rotation and translation. So basically, I have 6 degrees of freedom. Then I input it into a neural network and calculate just one scalar. That's the energy associated with the middle bar. So that gives me a scalar, and then I use backpropagation all the way, not just to the input, but all the way to the absolute coordinates of the triplet. Then I get a 3×1 vector, that is a force and torque acting on the middle bar. And we can prove that using this kind of formulation, like the pipeline, these force and torque are equivariant to rigid body rotation and the translation of the triplet. We can mathematically prove that. I will show later. So the second ingredient is called what we call subnet. So basically, this is to enforce reflection symmetry on the neural network. So reflection symmetry means that mirrored configuration should not change the elastic energy. So we construct the energy as a sum of all the involving reflection copies. So let's assume that this is the original configuration of the triplet. So of course, we need to calculate the relative positions between the bars, and then we also construct the reflected copies, like reflected with respect to y and x axes. This compound reflection is like reflection with respect to the origin. And then we have 4 copies, and we put those 4 copies in parallel into the same neural network, G theta. Here, theta is the weight of the neural network. Then we have 4 copies, and each copy will get a scalar. I have 4 scalars. I sum them up, then I get the final energy. And we can prove that this final energy, this single scalar, is like invariant to the reflection operation, the Carroll transformation. So if we combine these two together, the entire framework is like this. So let's assume initially I have 9 numbers, the absolute coordinates of the triplet. The first step is to calculate the relative positions between the bars. That will give me rigid body motion invariance. And then I do a normalization, basically balancing the numbers. And then I construct 4 reflected copies, and I pass them through the same neural network, which is basically like a MLP stuff, a dense net structure. And then I get 4 scalars. I take the sum as a single scalar. So this module gives me chirality invariance. And the output is the sum of 4 scalars. That's a single scalar. That is supposed to be mimicking the elastic energy associated with the middle bar. And then I use back propagation, take the gradient of the energy with respect to the absolute coordinates of the middle bar. I get a 3x1 vector, which is the force and the torque acting on the middle bar. Force involving the force in the x and the y directions, and of course there's a torque. So this entire workflow gives me energy invariance and the force equivariance with respect to Euclidean transformation. So that means, for example, this is the original triplet configuration. Then if I translate it, rotate it, or do any reflection, this entire pipeline guarantees that their energies are the same. Their elastic energy associated with the middle bar are the same. And that is called energy invariance. And force equivariance is like, let's say this is the initial, this is the force acting on the middle bar for the original configuration. If you translate it, rotate, if you rotate, then this force vector will rotate by the same angle. If you reflect the configuration, this force vector will also be reflected. So I want to stress that this kind of energy invariance and the force equivariance is guaranteed before you train the neural network. So you can randomly initialize this neural network module. This kind of properties will still be guaranteed. It's kind of like hard embedded in the workflow. It doesn't matter what are the weights of the neural networks. And there are, this is some details I want to talk about because we want to do the full scale simulation. So this is a boundary condition treatment. So in order to calculate the force using the triplet formulation to calculate the force for the AND bar, let's say this is a example of 30 cycle Slinky. We need to attach boundary ghost bars at the end. So for fixed boundary condition, if let's say the 30th bar is fixed, then you can simply throw away the ghost bars. But if this, let's say the 30th bar is free, then this ghost bar, the 31st bar is the exact duplicate of the 30th bar. And then you can still treat the 29th and the 30th and the 31st bar as a triplet and input into the Euclidean symmetry neural network. Then you will calculate the force acting on the 30th bar. This is just some details for the boundary condition treatment. Yeah. So with all the details combined, this is like one-step integration for the entire system. So let's assume that I have the Slinky state at any time instant, let's say Ti. So the first step is to separate the Slinky into a lot of triplets. And then I put all these triplets into the same Euclidean symmetric neural network. So I have to, of course, do all the like translation, rotation, invariance, construction, and chirality invariance, calculate the energy surrogates for all the triplets, and do the backpropagation to calculate the forces acting on the middle bars. And then I get the elastic energy for the entire Slinky. And then I add gravity force and damping force. Basically, you get the force. I'm sorry. Okay, I get a force assembly. Then I put that into an ODE solver, basically an ODE solver of your choice, like Roger 45, whatever. And then you can do the integration in time, get the Slinky state at the next time step. So taking 30 cycle Slinky as an example, basically I still do the convolution, but you instead of directly predict the solution at the next time step, using Euclidean symmetric neural network, we predict, we output the forces and torques on the middle bars. So we convolute along the Slinky. Basically, you get the elastic force vector, and you input that into an ODE solver. You get, after integration, you get the Slinky state at the next time step. And we do this iteratively. You get the entire trajectory for the Slinky, and that is supposed to be matching the ground truth trajectory. So if it's not matching, you update the weights for the Euclidean symmetric neural network. Here are some like conclusions. So eventually we can get 60 times computational acceleration compared to the ground truth. And this is like a comparison between the experiment and DR simulation and the neural network for the static deformation of a 76 cycle Slinky. And so the training data we use to train the Euclidean symmetric neural network is just 0.7 seconds of a trajectory of this 76 cycle Slinky dropping under gravity from a horizontal initial condition. And that 76 is a 3D DR simulation, but the material properties and the geometric like constants are calibrated by like a real Slinky bought from Amazon. So we only train the neural network using the first 0.7 seconds data, and we can extrapolate roughly to 2.5 seconds. It's very good prediction. And we analyze the learned energy field. You will see that the binding energy is not only a function of the binding angle of the triplet. So it's also a function of the stretching between the bars. So the energies are different. The elastic binding forces are also different. So that shows the energy. Basically, it captures the nonlinear interaction between the stretching and the bending for the Slinky automatically. And after training the neural network, we training on the 76 cycle Slinky, we tested on directly on a 40 cycle Slinky. And this one is like dropping from a horizontal, and this is a vertical dropping. Different initial condition, different boundary condition, orientation. So this is without changing, without further fine tuning or anything. And this is like we can also change the material property of the Slinky. Like we halve the Young's modulus. Of course, in this case, for the DR simulation, we assume we have the exactly the halved Young's modulus. But for the Euclidean symmetric neural network simulation, we simply divide the output force and torque by 2. So there's a strong assumption here that the calculated forces, they are proportional to the Young's modulus, but that's kind of reasonable in this case. So this is a like a fairly accurate simulation. It's just again that we don't further fine tune the neural network, just a 0 shot, and this is like changing the density. So we simply have the inertial matrix for the Euclidean symmetric neural network, and we also can change to different change to force boundary conditions. So for the 3D DR, basically we have 2 horizontal 0.25 Newton forces acting on the end bar, and for the DR simulation, we attach a horizontal 0.5 Newton force on the end bar. So you can see this is the simulation. So this is an ablation study. Like for the pure data-driven approach, I already talked about it. Like directly learning the solution field, it's good in training, but for testing is far from accurate. So that highlights the necessity of learning the derivative field. And the second one is what we call also ablation study. What we call it the force method. So this method uses a naive neural network without the invariance and the equivariance embedded, just a naive neural network to learn the coordinate and the force data pairs of the triplets. So we constructed a training data set with 1.8 million data pairs, and we train this neural network. The training loss is very low, but after training, we embedded in OD solver. So I'm sorry, you can see this is the result. Eventually, so after some integration time steps, basically the whole thing, I don't know, exploded. And this kind of like highlights the necessity of incorporating invariance and equivariance in the neural network. And the third one is what we call energy method. So this method basically it uses the same, exactly same architecture as Euclidean symmetric neural network, but it's trained on coordinate and energy pairs. So we also have 1.8 million data pairs in the training data set, and it also constructs the invariance and equivariance and use backpropagation to calculate the forces acting on the middle bars. And we also embed these forces in ODE solver. So you can see this is kind of like the result after some integration. The simulation diverges. So the difference is Euclidean symmetric neural network is trained under the neural OD framework. For the energy method, since you train it on the coordinate energy data pairs, no matter how accurate it is, eventually you will have some small errors. So those errors will accumulate as you do the integration in time. But for the Euclidean symmetric neural network, since the output is a trajectory and you are trying to match that trajectory to the ground truth one, it tries to find not only an accurate energy field and induce the force field, but it also wants that kind of field to be stable under time integration. So this kind of integration, just like an auto-regressive kind of like thing, training framework, it induces stability in the resulting energy field. So eventually this paper is published as cover on the extreme mechanics letters, and we have some. I wouldn't read through the conclusions, but basically we have the physics embedded in a Euclidean symmetric embedded in a neural network. We can, from a single demonstration, train the neural network and generalize to like unseen boundary conditions and initial conditions. And with some assumption, some would argue a very strong assumption that we can generalize to different Slinky properties like Young's modulus, density, and a different number of cycles. But like, what about like, if you change the radius of your cycle or you change the thickness of a coil? You can not simply assume that the calculated forces is proportional to these parameters. They are not proportional to the parameters. So if we want to generalize to all these further like cases, one possible remedy is that you can include such parameters as part of the input of your neural network. And let's say train on trajectories for just different cases or a collection of all these cases. But we want to go one step further. How about we don't assume their existence. We don't assume that we know what are the influencing physical parameters, how many are there, and their values. We don't assume anything. We don't assume anything. We just want to learn the dynamics of a collection of systems from data, from trajectories. So that will lead me to the second part. This is still under review, but I will briefly talk about it. So this is how to efficiently model a family of systems. So still, this is the paper on archive. So still we consider learning the dynamics of ordinary differential equations. I need to define some terms. So first one is system instance. That means one particular system with certain physical parameters phi. And the system family means that a collection of system instances that share the same form of dynamics but differ in their physical parameters. So one example is that you have this bouncing particle, a lot of bouncing particles. They are a system family, but let's say they differ in their particle elasticity. So they are, each one is a system instance. And we propose that it is a waste to only learn one system instance at a time. We propose a tool called interpretable meta-neural ODE, or AMOD, to learn and characterize the shared dynamics form of the entire system family. So you can see that there's a word meta here. So it's inspired by meta learning. So to distinguish between multitask learning and meta learning. So multitask learning is like you want a neural network model to learn different tasks while. So after training the neural network, it can perform well on different tasks. But in the meta learning context, I'm asking a neural network to learn different tasks quickly given limited data. So if the neural network can't do this, ideally it can be deployed to a new task with a very limited data and still learn that new task quickly. So this is meta learning technique context. For iMode, we have this kind of data scheme. So I have a lot of system instances, and they differ in physical parameters, of course. And for each system instance, I can like observe or collect several trajectories from different initial conditions, of course. And these collections of trajectories from this collection of systems is going to be my training data set to train a model to quickly learn different tasks. And we assume that this model knows which trajectories are from the same system instance, basically like the membership information. For example, these trajectories are from the system 1. But we don't assume any knowledge or information on the physical parameters. We don't know if an influencing physical parameter exists and the number of the physical parameters or the values of the physical parameters. We just have these trajectories. Two important like tricks or ingredients in the iMode method is called separation of model parameters and bi-level optimization. So this is the neural network used in the iMode. Y is the system state as usual, and here eta is like we call it adaptation parameters that accounts for variations across the system instance. So the concatenation of y and eta is going to be the input of the neural network. And this neural network is parameterized by the weights theta, of course. And we call this shared parameters. And the output is for second order dynamical system, this is going to be the force for that system. In general, for first order dynamical systems, it's going to be the derivative field. So why we call this adaptation parameters? Because for different system instances, we are going to adapt eta to that system instance. And this theta is, but this theta, the weights of the neural network is shared across system instances. So it is supposed to be capture the shared dynamics, the shared form of the dynamics in the system family. So the bi-level optimization is kind of like inspired by this original memo work developed at UC Berkeley. So from like, let's say we have an initial theta and eta value, and I have let's say 3 system instances. Then I will update this eta according to each instance in a few gradient descent steps, like I say 5. In 5 gradient descent steps, I will update eta to separate values. And then I will evaluate the gradient of theta at specific eta values. So the gradients of theta will be different because you have different eta values. Here, these gradients of theta are called instance specific gradient. And we sum them up to calculate the meta gradient for the initial theta value. So we will update theta using this meta gradient. So this entire bi-level optimization, because you first optimize eta, and then you optimize theta. Kind of a little bit confusing, but this entire bi-level optimization is translated into English is trying to find a good value of theta so that you can adapt eta, the adaptation parameters, easily. It's trying to find a good shared parameters theta to capture the shared dynamics form of the entire system family so that you can adapt these adaptation parameters eta quickly to each system instance. So I wouldn't go to the mathematical details, but we did have some approximation to make it computational efficient. So eventually, after training this I-mode neural network, the performance is that we can adapt to learn the dynamics of different system instances in very few gradient descent steps, like 5. So for example, here, for the single pendulum system, my only influencing physical parameters, effective physical parameter is the arm length L. And I can change the value of L to construct a lot of system trajectories, dynamics. And using this I-mode framework, I basically can adapt to each system instance with a different arm length, of course, in 5 gradient descent steps. And after 5 gradient descent steps, the adapted model is going to be an accurate dynamics prediction model for that system. So here I have like, this is a trajectory for different pendulums with different arm lengths. And the circles, there are predictions for the adapted I-mode model, and the lines are ground truths are perfectly matching. And for the bistable system, you can see we have 2 influencing physical stiffness parameters, K1 and K3. And I can vary the values of them. And still, I-mode is going to learn the dynamics of a specific system in just 5 gradient descent steps and do accurate prediction for unseen initial conditions. Yeah, and this is also true for the vulnerable system. This figure shows that the fast adaptation capability of I-mode to unseen system. So I'm giving one trajectory of an unseen bistable system to a naive neural network and an I-mode neural network. So you can see that the naive neural network is the same structure, but initialized randomly. And it starts from a very large loss and it drops in like 100 epochs. But this I-mode neural network can get a very fast decrease in the loss in the first 5 gradient steps. And that is roughly equal to 60 epochs for a naive neural network. And if you want to further decrease the loss, you can continue the gradient descent. But the mean point is the fast drop in the first 5 steps. And so after learning the I-mode neural, after learning, let's see, do I have time? Okay. Basically, the I-mode, if you analyze it, the I-mode adaptation parameter is physically interpretable. The value of eta is correlating. Let's see, I don't have too much time. Okay, is correlating well with the true physical parameters. Let's say for the single pendulum, it's correlating well with the inverse of the arm length. And for basketball system, in the 2-dimensional eta, you can identify 2 principal axes correlating to the increase of K1 and K3. And this is also true for the wonderful system. And we don't have time, so I'll quickly go. So this one it shows that you can read the papers, a lot of details, but basically we have a method to determine the optimal dimension of eta. You don't need to preset the dimension of eta. You can vary it and you can find the optimal one. And the optimal one across a lot of systems, we prove that it's just the true dimension of the physical parameters. And we can build this neural gauge functionality. Basically, if after learning the I-mode neural network, you construct a latent space of the dynamic adaptation parameters, and then if you know the true physical parameters of some of the system instances, you can construct an invertible transformation between the latent space and the true physical parameter space using a neural ODE. And then if you give a trajectory of an unseen system, you can feed the I-mode neural network with that trajectory, and the neural network will quickly adapt this eta parameter in 5 steps to learn that dynamics of the new system, and you can get the value of eta, pass it through this invertible transformation, and that will give you the true physical parameters of that system. So basically, this is a virtual instrument to measure the physical parameters of a new system. And this entire pipeline from seeing the new trajectory to eventually giving you the physical parameters we measured across a lot of systems, it's just 2 seconds. So it's a virtual instrument. I would skip this one. You can build the invertible transformation using neural ODE as a diffeomorphism. So we also applied this fast adaptation on the Slinky system. So for this case, I have 4 Slinkies with different Young's modulus. And it's a 40-cycle Slinky with both as fixed and dropping under gravity from a horizontal initial condition. And for each Slinky, I only have 1 trajectory. And I'm asking the I-mode neural network to learn the quickly adapt to the dynamics for each Slinky. So I only use 2 adaptation steps, and learning the 4 cases, 4 Young's modulus Slinky. Then after training the I-mode, I ask it to adapt to an unseen Slinky of Young's modulus 56 gigapascal. And this is like the adaptation parameter, adaptation results is matching pretty well after just 2 adaptation steps. And then we evaluate after adaptation, basically we fix the neural network and evaluate on a different boundary condition. You can see that this is ground truth, like vertical dropping with 1 and 3. And this is a prediction by the I-mode neural networks, roughly accurate. And I want to emphasize that this is kind of like with Euclidean symmetric neural network embedded, because this I-mode inspired by the MIMO is a total model agnostic approach. So you can embed any neural network architecture of your choice into this framework. It doesn't matter. So we embed the entire chapter 1, wrap it up in the framework. All the Euclidean symmetry, the energy invariance, conservation, force equivariance, the backpropagation within backpropagation is all included in this framework. So for during adaptation, for each adaptation step, the resulting neural network will be a Euclidean symmetric neural network. That's why we can directly, after adaptation, generalize to different initial condition, boundary condition, orientation, and different stuff. Oh, so that basically concludes my talk. So for the Euclidean symmetric neural network, I would summarize in one sentence: is neural OD plus physics prior. This will give you data efficiency and generalizability. And for the interpretable, for the I mode, basically is truly model agnostic. You can embed any favorite physical prior, and you can use it to discover physics. You can use it for faster adaptation of the dynamics of the system, and you can use it as a neural gauge to virtually measure the physical parameters of an unseen system. Yeah, that's all. That's all. Thank you.
Thank you so much, Qiaofeng. That was really cool. A virtual clap. Well done. So I'll open the floor for questions. If there's any, which you can do so through the chat, or ask. You can also ask in person. I had a question in the meantime with regards to the first approach, with the Euclidean symmetry approach. So if you were to reference real observed data from an observed system that contains noise, for example, how does your approach deal with that? Because currently you're not, I think you're not dealing with extra forcings on the system. Let's say there is external forcings.
First one is like noise in the in the measurements, right?
Yeah, correct.
Yeah, yeah, we need to consider that currently. So I would say that we can fairly, we don't have that in the paper, but we can deal with that because we are constructing a reduced order model that kind of like already contains is equivalently some noise in the measurements, because you can not fully recover the dynamics of the full order model from a reduced order model that contains some kind of deviation already.
I see.
Yeah.
Actually, so also on that. Oh, sorry, go ahead, please.
So the second is additional forcing. My colleagues at UCLA, like you can check their work. They are okay. I need to go back to the very beginning. Professor Khalid and his students, basically my previous colleagues, they are doing a lot of things like incorporating a fluid structure interaction on like slender rod structure, basically a soft slinky, like the bacterial flagella, basically it's a soft slinky. They are focusing on that, and they publish a lot of work. You can check their work, Professor Khalid.
Thank you. Yeah.
Yeah. You can deal with the external forcing, of course. And
another question about the reduced order modeling. So from on the left hand side, right? So that's the previous time step. When you reduce, can you utilize the eigenvectors that, since you have the physics that you are specifying, right? The eigenvectors from your dynamic operator, from the dynamic system, they actually are meaning something, because you're doing a unsupervised learning, I guess, right? So like some form of PCA or some SVD based reduced order modeling. Can you use the eigenvectors from the physics directly? So you can easily obtain those eigenvectors.
You mean for the Euclidean symmetric neural network?
Yes. Yeah.
We didn't use PCA. So the Euclidean symmetric neural network, the encoder and decoder.
Right. Sorry. Yeah.
Yeah.
It's kind of a deep learning. It's a deep learning encoder or decoder?
No, it's like physical. I don't know. It's kind of like a naive geometric. It's not learnable. It's not a neural network.
Oh, right. Okay. I wasn't sure about that. Okay.
Yeah.
All right. Do we have any questions in the audience? It seems you were very clear. Okay. So without keeping anyone, I guess we can call it a day. Qiaofeng, I'd like to thank you a lot for joining us today and for sharing your work. This is really cool. I really enjoyed this myself as well.
Thank you.
And I'll let everybody know that we will upload the slides onto the website, which also we are in the process of migrating to Alan Turing Institute's more formal website. So things are a bit more standardized and a bit more formalized. So cool. Thanks again, Qiaofeng. I'd like to say have a good day to all, and we'll see you next time.
Thank you for having me. Yeah.
Oh, it's our pleasure. Thank you.
Thank you. Thanks again.
Bye,
Have a
everyone.
great time.